Okay, so we can start. We have Emanuele Castorina from Milan University, and he will talk about 21 centimeter in the 20s.
Thanks, Diego. Thanks for the opportunity to give this talk. I'm sorry I couldn't be there. I see that you guys are having a lot of fun. So today I would like to tell you something about 21 centimeter. And this is a very broad subject I was asked to talk about. So everything I'm going to say is really a reflection of my personal biased view of this field. Oops, so now it doesn't switch anymore. Okay, is it moving? Yes. Okay, so when we talk about 21 centimeter, usually we have in mind three different epochs during the history of the universe. So there is one very early phase, which we call the Dark Ages. So redshift higher than 30. And more or less here, we're really probing the true primordial density field in the linear regime. But of course, this is not yet accessible to current technology, especially from Earth. But then there are two other regimes. One is the cosmic dawn EOR. So let's say between redshift, I don't know, something like 20 and redshift 6. And so this is the time when the first galaxies, stars and galaxies form. And there are processes here which are mostly driven by the astrophysics of this object. Although, as we will see, there is interesting dark matter physics that one can try to constrain. And there are experiments looking at this particular range of redshift, like HERA, several pathfinders of SKA and SKA itself, and of course, global 21 centimeter experiments. After ionization, the little amount of H1 which is left, neutral H1 which is left in the universe, resides into galaxies where it is self-shielded from UV photons. And so here, basically by measuring 21 centimeter, we're really just doing a galaxy survey, but rather than being in the optical, it's now in the radio. And so there are several experiments which are actually targeting 21 centimeter in this range of redshift, like CHIME, HIRAX, TNLI, GBT, and also several of the SKA pathfinders. So before we go into the sort of science that we could do with these experiments, I think this is not looking quite okay. Maybe this way will look better. But before we go into the science, I think it is important, and this is something which has been brought up in the previous days of this meeting. We discuss about the backgrounds and the foregrounds and what are the theoretical systematics in any kind of searches for new physics that we do. And so this is particularly important for 21 centimeter. I don't think I'm breaking news to you, but all these current measurements are completely dominated by foregrounds at this moment. So when we do radio astronomy, there are two ways we can measure the signal. One is in this autocorrelation regime. So you have dishes, antennas, and you measure the intensity in each antenna and you sum them up. And so this is sometimes also called a single dish autocorrelation. And so the problem of doing high redshift cosmology in this mode is that the resolution of your experiment, of your map of the universe, depends on the size of your antennas. And so basically, if you go to high redshift, you end up, with requirements of like antennas which have to be kilometers wide to have resolution which is the order of 10 megaparsecs. This is clearly unfeasible. The other way, which is what most all, let's say, current experiments are trying to exploit, is using interferometry. So this is a design, this is a rendering of HERA. And so you see that there are all these antennas and they're closely packed. And basically what you measure is the time delay between each of these antenna. And in this case, the resolution is given by the longest baseline. So the longest separation between two antennas. And so in this way, you can really measure small scales, even up to very high redshift. Interferometry works this way. And I mentioned this slide because this is going to be very important when we discuss foregrounds later on. So the observable here is really what we call a visibility. So this is time average of the electric field which goes within each antenna multiplied by some beam. So this is the IJ. And so what you have at the end of the day is really a Fourier component of an image. So this measurement which works directly in Fourier space. And this is widely used for to do very small scales measurement. It has been used, for instance, by ALMA and VLA, and also by the Event Horizon Telescope to the image of M87. And so what you end up measuring at the end of the day is, as I said, is Vij, which is an integral over some direction of the sky of the true signal, which is your intensity, times the beam, times this complex phase, which has to do exactly with this time delay between two antennas. And so let's start after this very short recap of what's going on with the lowest redshift range, which is the one I'm mostly familiar with, so redshift less than 6. So why would we want to do it in the first place? So the reason we want to do it is that, let's say by the end of this decade, or through this, the middle of this decade, we'll have a very comprehensive view of the universe at redshift less than 2 from optical and near infrared surveys. And the question is, what do we do next? What's going to happen afterwards? And if you look at the numbers, it turns out that it is very complicated with optical and near infrared to go beyond redshift 2 and observe very large fractions of the sky, retaining a very high sampling of number of galaxies. And both these two things are important. Let me just briefly mention why. Because volume in cosmology is really like center of mass energy for a collider. Because the larger the volume, the error bars then go on cosmological parameters go down with the square root of the volume. And if you look at how much volume there is between redshift 1.5 and 6, and how much volume is there between redshift 3 and 1.5, there is more or less a factor of 5. So you gain this factor immediately by going to higher redshift. And of course, the higher the redshift, the more linear the field is. And so all our perturbative approaches work much better. And so you can really improve a lot the constraint. And this is complicated in the optical, as I was saying, because you really have to measure a lot of galaxies in this volume. And this is, if you allow me to continue with this analogy, this is like luminosity for colliders. It's not enough if you have 100 TV, you need to have a lot of luminosity to collect a lot of events. So just visually, how this looks like if you do it in the optical, let's say. So this is the dark matter density at redshift 3. So this is how the sampling of this dark matter field would look like if you had billions of dollars and you could get a spectra for each of LSST galaxies which are measured photometrically. This is, of course, completely unattainable. And this is what you could get with some futuristic optical near infrared instruments. And so you see that already this is quite a sparse view of this system. But when you go to redshift 5, basically the sampling is becoming so sparse that it's very hard to reconstruct density fluctuations in the universe. And so the way out is to really just measure the integrated emission at a given frequency. And you can do this with several lines. The most promising really looks like it's the 21 centimeter line. And so this is like the CMB, but it is now in 3D. And so all our estimates tell us that this problem of sampling enough number of galaxies will be completely solved by this sort of intensity mapping arrays, because the noise equivalent of this instrument will be of the order of 10 billions of galaxies. So this is more than 100 times more galaxies than you will get with an optical survey. So this looks great. So the question is why haven't we done it already, and why is not everybody working on it? The question is because it's tough and there are no detections yet. So what we have so far are measurements in cross correlation between the GBT telescope and an optical survey. This is 3 types of galaxies. And so there is this measurement in cross correlation, which is very exciting, but we do not have yet any measurement in autocorrelation. And the reason we do not have, let me just mention the observational status. So I was saying this before, these are just some numbers about other experiments. And so the reason we do not have any measurement is what I think you know already, is that the foregrounds are much brighter. And this is the price that you pay when you take all integrated emission within your antenna. And in particular, the usual ratio that we have in mind is about 10 to the 4, 10 to the 5. So it is not really a fundamental limitation of the approach. But it tells us that in order to be able to make a detection and be confident in this detection, we need to understand both the instrument and our data analysis at the level of 10 to the -4, 10 to the -5. it's even worse than this. And so I just want to mention a number of complications, which are real world complications, which enter in all our forecasts when we try to see the reach for new physics of some experiments. So one of them is this terrestrial interference. So this is us with our cell phone antennas and television and so on, which are very radio loud. And so this is the reason why all these experiments are built in regions which are very radio quiet. And so beyond these cartoons, let's just look at the map of the signal and what in the foregrounds. And so you see this is the unpolarized, polarized foreground. This is the 21 centimeter at redshift around 1. And so the scale, it's really what's striking here, because the foregrounds are very bright, around 700 Kelvin, whereas the signal we're looking for, it's actually on the order of hundreds of micro Kelvin. However, what you see from this slide is that the signal contains a lot of structure, whereas the foreground is pretty smooth. So what you imagine is that if you do a Fourier transform, then the cosmological signal will populate all sort of Fourier modes, as we expect, whereas the foregrounds will only contribute to low K, which are the largest Ks, and those are the smoother ones. This is more or less true. And so here you see, again, simulated data. And so you see this is the power spectrum, and this are going to be your error bars. And at some point you add the foregrounds, and so you lose the ability to measure the very low K. It is, however, much worse than this, because the instrument response will actually make this foreground percolate to much higher K. And so this is an effect which is known as the wedge. And so although you naively think that your foregrounds are living below this black line here, actually they are creeping in and populating all our much higher values of K. And so this is, again, not really a fundamental limitation, but it's something that we have to keep in mind when we forecast and especially when we do data analysis. And so we're really confined to make observations in this range. And so all I'm going to show you next, these are the kind of restrictions that we're going to have on our signal. And so this is a plot in the K parallel, K perpendicular plane. And so everything in the blue is removed by the foregrounds. Everything in the red and in the gray is removed by the fact that we have good models of perturbation theory, but let's say we could do better. And so we're also removing all those modes. And so really we're only looking at signal in this white region of this plane. And so based on this consideration, we came up with this proposal for a stage 2 21 centimeter experiment, which we call PUMA. Which is a several thousand dishes of 6 meters in hexagonal packing with the filling factor of a half. And so the numbers that come out, before we look at the numbers, let's just look at visually how an experiment like PUMA would look like at redshift 3. So this is what we saw before. So this is how PUMA would look like. This, you see immediately that it's much closer to the true dark matter distribution, which we would like to measure. The stripes here that you see are due to foregrounds. If you go to redshift 5, this is how PUMA will look like. So you start seeing effects like smoothing and finite resolution, but still this is a much better map of the universe as opposed to anything that you can do in the optical or the infrared. So let's look at some numbers. So this is the improvement relative to the state of the art we will have by the end of this decade, which is going to be Planck plus the Simons Observatory plus DESI or Euclid, combination of two. And so for several parameters, PUMA in some optimistic or pessimistic scenarios in terms of foreground will actually improve substantially the parameters. And in particular, there are a few things I would like to highlight. There will be measurements of the expansion rate of the universe to sub% accuracy down to redshift 6. It's basically going to nail down any possible early or late dark energy scenarios. There's one thing which I think this crowd cares a lot, which is this measurement of an effective. And so we know that when we allow the helium fraction to be a free parameter, the bound on an effective degrades a lot, and this is due to some degeneracy in the damping tail of the CMB. But the large case structure in 21 centimeter in particular cannot care less about the value of YP. There's no damping tail here. And so if you now combine large-scale structured data with CMB data, even if you marginalize over YP, which means that you're assuming that the number of relativistic degrees of freedom could be different between BBN and recombination, you will still be in the ballpark of 0.03, 0.04 for delta N effective. There would be a high significant detection of neutrino masses, regardless of how big your parameter space is. And this is pretty important, both for neutrino mass and I guess for what Julian is going to mention later. And an instrument like PUMA is the only instrument that, at least on paper, could achieve an uncertainty on FNL equilateral of order 10. Then we move on. So Xing and Chen yesterday mentioned features. I think this is pretty important. And so you see here the constraint that we could obtain on the amplitude of this feature as a function of the frequency of this feature with several surveys. And what we get from this plot is that the large-scale structure is much flatter than the CMB at doing that, in particular because CMB already has a lot of oscillation and there is a damping tail. And large-scale structures can do much better, and in particular, these ones in orange, which are the 21 centimeter surveys, are the only ones which would get closer to this light blue line, which is the cosmic variance limit of the large-scale structure. This is basically the best possible measurement that you could ever get up to redshift 6. So this is a pretty impressive bounce. But I don't want to continue talking about each individual constraint that we could do. I guess one way to summarize what a survey like PUMA or in general 21 centimeter surveys could do at low redshift is to make one of these sort of propaganda plot where you take measurements from different probes and you put them on a plot of the power spectrum at redshift 0, see which scales are probed by different experiments. And so you see that by measuring the high redshift universe with a survey like PUMA or others, you really have incredibly tiny measurements of the power spectrum up to K of 1. So wherever is your new physics model of dark matter, if it changes the power spectrum up to K of 1, you will be basically doomed by measurements of PUMA, or you will have detection in the optimistic scenario. One thing which is also worth pointing out is that going to higher redshift, we will have this tiny uncertainty at redshift 1, much smaller than uncertainty we have from the Lyman alpha forest, and in a regime which is much more under control in a perturbative sense. So there will be no need to rely on simulations like we did for the forest. So these are some thoughts that I have on low redshift. We need to see a detection because we haven't seen a detection, and so this is really what everybody's waiting for. We need to show that this is feasible. There are questions which are very important for the future, in particular to sort of realize all these promises that I mentioned in the previous slides. We need detectors arrays which have of the order of 10,000 antennas. And so this cannot be done with current technologies. Just to give you an example, the instantaneous bandwidth of such arrays is much larger than the one of Atlas and CMS, even in high luminosity configuration. And then, of course, there are questions about the theory, which is very much under control. But when we push to smaller and smaller uncertainties, then we also have to start questioning the theory again. And in particular, there's one very important question, which is that we need the bispectrum of galaxies. So when at one loop, if we want to measure one of the longest length beyond local shape, and it's not yet available. So let me move on. How much time do I have?
I think you can go for other 5-10 minutes.
Yes. Perfect.
We are relaxed with the timing.
I know.
We gave up.
I want to keep.
We gave up by now.
Yes, I want to keep up the tradition of being massively over time, especially these days. So let me talk about the UR now. So now we're looking at redshift, let's say between 20 and redshift 6, and there are various things that happen. There is a lot of physics going on here. There is a first regime in which the Lyman alpha photons are the ones responsible for 21 centimeter absorption. So then it's going to be the X-rays, and then finally the UV, which are going to completely ionize all the intergalactic medium. And so you end up having a relative brightness temperature to the CMB, which looks like this. So there will be absorptions and then and so the depth of this trotty is basically given by the relative abundance of Lyman alpha and X-ray fluxes that you have here. Of course, I'm giving an oversimplified view of what's going on. Contrary to the low redshift universe, here we have a detection. And in general, I would like to say that the high redshift universe is in much better shape compared to the low redshift in terms of capabilities and an analysis method. I think we should borrow more from high redshift and bring it to low redshift. So there is a detection, and this is edges. And one way to summarize edges, at least for me, is that it caused a lot of excitement in particle physics, but a lot of skepticism in the 21 centimeter community. Hedges team has been great, very responsive. They put all the data public. People have raised concerns. They went back and checked a number of things. So this is really a fruitful discussion that is happening in the community. And it also motivated a number of other experiments to go and look for this excess, which is at 78 megahertz, around redshift 17. Is a half a Kelvin, and it's supposedly 2 times larger than what we were expecting. Although what we were expecting is a bold statement, because what we were expecting was something like this. And so this, I think, is an underestimation of our current theoretical uncertainties into this brightness temperature. This is a plot from Corner 2017. And so you see this mean brightness as a function of this ratio between the X-ray and the Lyman alpha flux. There is, several factors in uncertainty, and I think it's actually much bigger than what we're seeing here. And if you're worried that this uncertainty is mostly driven by astrophysics, this is certainly true. However, there is also a lot of uncertainty which is just coming from things we don't know even without thinking about astrophysics. Just to give an example, we don't really know how many halos of dark matter are there at high redshift. We have no idea, we have no predictions, and simulations, full embodied simulations are very expensive at those very high redshift. And so just uncertainty in how many halos you have, regardless of the astrophysics, make basically this prediction uncertain than more than a factor of 2. So this is a problem. And of course, David Courtin the other day was mentioning this nightmare scenario where any new physics that we can possibly come up with, there will always be some astrophysics parameter that we can tune. And so I'm worried this could be the case. So we really need to make sure that this is not happening. And so we need to find recipes to avoid something like this to happen. And I have some comments toward the end about this issue. So there are measurements of brightness temperatures, detection actually in edges. There are also measurements of power spectra. And so you should not get depressed by this plot. So these are current upper bounds from of the power spectrum of 21 centimeters as a function of redshift in this range of scale. And so although we are a factor of like 2 or 3 orders of magnitude away from where we expected the signal to be, what I would like to take away is that over the course of a few years, we really have improved orders of magnitude compared to where we were before. So really we're making progress at a fast pace. And this progress is incredible, at least for me. The best upper bounds are now coming from HERA. There was a paper which came out a few months ago by the HERA collaboration. And so these are the best upper bounds that we have. And these have been obtained in only 39 antennas out of more or less 350, and only 36 hours of integration compared to more than 1 order of magnitude that we get at the end. So these are the data. And even though they don't have a detection, they've already been able to put quite interesting upper bounds on astrophysics of the IGM, of the X-ray, star formation rate, and so on and so forth. And here I'm going to steal some plots from Julian. And he's heavily credited for all this work. And so you can already put bounds on milli-charged dark matter interpretation of the edges anomaly. And so here you see that basically this blue area, which is in this plane of charge versus mass, the one favored by edges, is already excluded by Hera upper limits if you assume that there is no heating taking place between redshift 10 and redshift 17. So this is already quite interesting result, despite not having a detection of the 21 centimeter power spectrum itself. You can, without a detection, you cannot exclude the other possible explanation for edges, which is that you have some excess radio background in the Raleigh genes tail of the CMB. For that, you will need a detection. But still, this is quite promising. And so, looking ahead to the future, I want to discuss some other things that I guess I think this 21 centimeter power spectrum is going to be very important for. So one outcome of all this measurement is going to be a constraint of tau on the optical depth to realization. And already this tau is the limiting parameter in constraints of neutrino masses and other light relics. And so it's very hard to improve on this tau because you need very low well CMB experiments. So you really have to wait for LightBird, or you could do it with the NEOR experiment, which directly measures tau. And so here you see how the blue, which is again this sort of S4 plus Planck plus DESI, sort of state of the art in 10 years, how this bound on mu improves if you add the 21 centimeter information on tau. So this reflects both in mu and also in light relics. And I don't want to go into the sort of all possible models of dark matter that you can exclude or you can constrain. Basically, anything that changes the power spectrum at scale greater than 1 will change its power spectrum at order 1. So let me just summarize the power spectrum in a plot. This is again from Julian. So this is a 21 centimeter spectrum at redshift as a function of K. And so you see that the Hera will measure this power spectrum here in this range. And the shape of this power spectrum depends on physics, as I was saying, at very high K. So here you can do two things. You can either say that you're going to for a fully simulation approach, so you just try to simulate everything. And so the shape of this power spectrum will depend on the small scales. And so you could get stronger constraint on dark matter, or you could hope that there is some other way of doing it. And so this would require some perturbative approach. I guess, Julian, you should do like one of these propaganda plots from this also for Hera. I think this would be very interesting to have a look at. So let me summarize my thoughts on this high redshift stuff. So we will have, I'm pretty sure about it, we'll have detection soon, most likely from Hera. And there will be questions then that we need to answer. One is what will happen to edges. It's going to be confirmed by experiments like Sarah's, or Hera itself is going to exclude it. There is a question, which is how do we build confidence in one of these detections? One advantage of low redshift kind of 21 centimeter cosmology is that we have galaxies in the optical that we can cross-correlate with, and so remove the program from this cross-correlation. There's not much to cross-correlate with at high redshift, so we really have to sort of do our best and be sure that this is a detection. On the theory side, there are really these two questions for me. They're very important, and maybe this is for discussion. So how much can we trust the simulations in the search for new physics? Is there any range in redshift and K in which the cosmic dawn EOR is kind of perturbative? Because if we do have perturbative approaches, then we know how to sort of put all these astrophysical uncertainty in some coefficients, and we can marginalize over them very robustly. This is what we do in galaxy orbit already. We don't care about the details of galaxy formation, we just have a number of Wilson coefficients that we marginalize over. And so initially I was a bit skeptical this was possible for cosmic dawn EOR for reasons which I'm happy to discuss later. But somehow recently there has been some progress, extremely interesting progress starting from this paper, which showed that maybe this is possible. And this will really be a game changer in searches for fundamental physics, because now we will not have to worry that much about astrophysics anymore. So this is my summary. So we're making progress toward detection, or however, we have things we have to figure out in order to exploit the unique possibility that 21 centimeter offers for new physics. And in particular, they are both in terms of the instruments, how do we scale this up to order 10,000 arrays, and how we can also robustly marginalize over uncertainty. I haven't talked about dark ages, but maybe some of you know, I know some of you are involved. There are proposals submitted to NASA and DOE to build arrays on the far side of the moon. Those are extremely cool, and we can also talk about those later. Let me just conclude with a positive note, and then I will shut up. So I guess we can learn from history that we should not be so negative about making this detection, even though we are a few orders of magnitude away. And in particular, I always bring up what Jim Peebles said in this review in 2012, that after he predicted the existence of acoustic peak in the CMB, moved on, because he thought that those would be never detected. And now we see how the story continued, and we have this incredible Planck map. So that's all I had to say, and thank you for your attention.
Thanks, Emanuele. Questions?
Hi, Emanuele. Thank you for this really nice talk. I have a question about this this chart you showed comparing to Planck, and it had different spokes going out, you know, for delta effective and whatever. And you mentioned delta effective could do sort of 0.3, 0.4.
0.04.
Yeah. So 3 or 4%. I'm a bit surprised. Like I haven't thought about this 21 centimeter possibility seriously. The cartoon in my head is that it's this incredible data trove, like you said, 3D, etc. And I would have expected that the ultimate limit of a delta effective measurement is much better, because you have so many more modes in theory that you can access than the CMB. Because for the CMB, if I recall, at sort of the few thousand mode numbers, the cosmic variance limit of delta effective is like 1 or 2% or something, if I recall correctly. So the cosmic variance limit in 21 centimeters should be way lower, no? So could you, how far could you go in principle? Or is this the sort of principal limit, do you know?
Right, so let me give you two answers. So one thing is that if n effective was the only cosmological parameter that we are looking for, without, you know, if all the others were fixed, you would be right. But once you have all these other parameters you have to marginalize over, then basically the final constraint is given by the degeneracy with the other parameter, not really anymore by the number of modes. So there is this consideration. Consideration number two is that although we hear a lot saying that large-scale structure contains many more modes than the CMB, this is not true. Because we have to stop at, let's say, at some scales which are perturbatively in the large-scale structure. And so we have to stop at k of 0.0 few, let's say, certainly k less than 1. Whereas in the CMB, you can go all the way to L of a few thousand. And so if you just work out the math between going to L of a few thousand or stopping at k of 0.2, these are more or less comparable. So DESI has more or less the same number of linear modes than Planck, although this is 3D. And the same can be said about SOARS 4 or Next Generation Galaxy Survey. So they contain similar amount of number of modes. The good thing is that they are orthogonal in parameter degeneracy. So this is one case in which the sum of the two is the combination of the two is bigger than the sum of its parts.
I see. So is that because in the 21 centimeter data set, some modes are already nonlinear, and that's why they don't give you this clean information?
Yes. Yeah.
I see. Okay, thank you.
So I see there are questions from the people online, so you can just unmute yourself and ask. I think I saw Cora and possibly others.
Okay, a quick question, Emanuele. You say that the edges anomaly would be cross-checked by a forthcoming experiment, but you didn't give a time scale. Very roughly, do you have some idea of the next experiment that will check this?
I think the best in line, to my knowledge, is SARAS 3. There were already two previous versions of SARAS. This is an Indian experiment, and I think it should come up eventually. I don't know about the time scale. Of course, with 21 centimeter, it always takes much longer than anticipated. So I remember talks a few years ago that this was, coming out soon, but then it didn't. So
okay, but it will be before SKA, I guess.
Oh, of course.
Yeah. Okay. Okay. Thank you.
Yeah. Hi. Thank you for the very nice talk. So I have a question about Puma. So a lot of the impressive constraints that you mentioned about Puma really come from the optimistic Puma. Not to say that Puma would be great, but I just wanted you to tell us clearly the difference between what you call optimistic Puma and you call pessimistic Puma. Just to know if the pessimistic is really the one that we should be expecting, if they're realistic or not. Right.
So let me be even more pessimistic and tell you that because we do not have a detection yet, things could be much worse than any pessimistic scenario that we assume in our forecast. So the difference between the pessimistic and optimistic has to do with the wedge. So whether you have sort of full wedge that you cannot do anything about it, or whether you can restrict this wedge to the sides of your primary beam. So this is the main difference. How much you can dig into this wedge, if it extends all the way, or if you restrict it to the primary beam size. So this is the main difference.
And that relies on also on our knowledge of foregrounds.
That yes, and it relies a lot on calibration. It relies a lot on calibration because if you know your beam perfectly and you know your foregrounds extremely well, then the problem of the side lobes can be reduced. So you can hope that the wedge will be confined to the primary beam size. But this is an important question. Of course, I agree with you that from this plot, sort of the pessimistic Puma doesn't look overwhelming. But this is only in this sort of combinations of parameters. I guess the power of something like Puma or 21 centimeter sub is really that you will have these maps at redshift, 3, 4, or 5 that look like this. And so there's a lot of other physics that we could do, which is not yet, which we cannot really encapsulate in these few parameters.
And since we are at it, you also claim that the only way of getting FNL equilateral about 10 was with Puma. What about Spherex?
I think Spherex is going to have a very hard time doing anything beyond local because the redshift error on each galaxies are very large. So basically you smooth out the signal immediately after the peak of the power spectrum. So it's very powerful for local. Certainly this is much more powerful than Puma for local. But for equilateral, which you really need to go on the right side of the peak of the power spectrum, you need something which is spectroscopically or 21 centimeter.
I see. So their claim constraints, at least at the level of the forecast, are worse than FNL equilateral of 10?
I think so. I might be wrong. Somebody has the number on top of their heads.
Okay, okay. I was just curious. Good to know.
For local, they're certainly much better.
Thank you.
But just to tell you, the number of the S4 constraint on FNL equilateral is over the 20. So this is a factor of 2 better than could be a factor of 2 better than CMBS4. If we work out the bispectrum at one loop, which is the big question here.
Thank you.
Ciao Emanuele, sono Paolo.
Ciao Paolo.
Ciao. So I didn't get what is the status of Puma in a sense. Is it something like an intermediate step towards SKA or it has a different role?
Right. So Puma was something that so the history of Puma is the following. So there was a cosmic vision dark energy program run by the DOE, which sort of was asking for futuristic cosmological surveys, and 21 centimeter was one of the 5 avenues that was realized that was thought as promising, and so we came up with this white paper. Then we submitted also to Astro 2020, so to the decadal process of astronomy, and so this is at this stage is a proposal and is completely independent from SKA. I need to tell you that Puma didn't do extremely well in the decadal survey. So it was certainly not ranked as something that we should build tomorrow. So the cosmology experiment that came out of ASTRO 2020 was CMBS4. There are discussions about other 21 centimeter instruments at higher redshift for cosmic dawn hypercompletionization. There will be a decision within DOE later within SNOMAS, and we hope we can get something to sort of start doing our R&D for PUMA. But it's completely independent from SKA. And the reason, I can tell you the reason why it is independent from SKA, because SKA is an observatory, so it will do a lot of things, a lot of exciting stuff. But when you want to do cosmology at sort of this level of precision, you need something which is custom built for cosmology. So we cannot do all the other exciting science that SKA can do with PUMA. We can only do we can do cosmology extremely well. Not all the other things.
I see. Thanks.
Just a design issue.
I also have a question, Emanuele. So can you go back to that plot that you showed about the milli-charge?
And this we ask Julian then.
Well, worst case, we ask you, Julian.
Yes, exactly.
Yeah, so here, okay, I see, okay, good. No, sorry, I misread the scale. So, but the message here is that, I mean, there were really like very few new physics models that could like fit this excess. I mean, assuming that is that is even real. Mm-hmm. So, could like a non-observation by ERA just exclude these few examples, you know, independently?
The one that survived, you mean?
Yeah, exactly, because there are very little example, right? So independently on like any experimental confirmation of edges, that would be of course like welcome, but also maybe challenging.
Mm-hmm.
Of course, you could just reinforce your theory prior against any new physics just by this ERA constraints.
Of course, you know, to exclude that, you would need a model that predicts the shape of the 21 centimeter experiments in these few models that survive. And I'm not sure that is yet available.
No, it's not. It's not. That's
and
yeah.
And as you know, I think that if you compare those models to low redshift data, they will be excluded anyway. It's just that we haven't done it, but I think they will not survive.
But to answer the question more precisely, like if, you know, we have some idea of, given that edges is deeper, the power spectrum should also be larger because it's proportional to the global signal squared. Yeah. So if Hera had the same quality of data at redshift 17 instead of redshift 10,
of course,
there will be no caveat about the heating. You would just say, within our knowledge of astrophysics, these models are ruled out.
Exactly.
But the problem is that
that's
Hera hasn't reached redshift 17 yet. So like that's coming soon, hopefully. But for now, it's redshift 8 and 10 that they've been able to probe well.
Okay, thanks. So if there are no other questions, we thank Emanuele again.